Chapter 8, number 66D, MO for molybdenum 3+. And for this question, the question was asking you to write the electron configuration for this. And first of all, we need to find what element number is this, and this happens to be element on our periodic table. So element number 42. So it has 42 electrons normally. But in this case, it is telling us that we have only a charge of 3+, meaning I need to actually remove 3 electrons from this, and this is going to drop it down to 39 electrons. So when we write the electron configuration, we write it for 39 electrons only. All right, so electron configuration, again, we can read the periodic table, and I know that light is in the way there. No way around that for me, fortunately. So we're going to go 1s block, 1s2. So we would write 1s2. 2s, second row, so 2s, 1, 2 blocks, so 2s2. We go across and over. That's the 2p block, and there's 1, 2, 3, 4, 5, 6, so 2p6. The next row, 3s2, 2 blocks, 3p6, and then we come to 4s2, and then remember that this is the D block here in the center, the transition metals, and the D block is the row that it is on minus 1. And the F block is the row that it's part of, which is normally part of row 6 and row 7. And so the F block is the row that it should be on minus 2. Okay, so that means this is a 4F group, and this is a 5F group or block. Okay, so if we continue back, we were at 4s2. We're going to go through the D's entirely, and again, this is off of the row, so this is 3D10, and then we're back to the 4th row, 4P, 1, 2, 3, 4, 5, 6. Then we're going to the 5th row, and on the 5th row, we've got 5s2, followed by 4D, 1, 2, 3, 4. Okay, that's normal for molybdenum, MO, right? So how then is it different? Do I just cut back to 39? Not quite, because when electrons are lost or gained, they're gained to the valence shell. And if I look at this, this is the valence, the 5s2 level. So this is going to be eliminated. It's going to lose 2 from there. And then, whoops, let's see here, I did 4D. And then it's going to lose 1 from here. So this is going to go down to 3. So a total loss of 3 electrons, giving us the 3+ charge and where they're coming from. Now typically when it is shown or given to you on an exam like the AP exam, this is the correct filling order. However, they're going to rearrange and group it so that the 1s are grouped together, the 2s are grouped together, the 3s are grouped together, which means 3p6, and then I have this set here, 3d10. Then the 4s are going to be grouped together, So it's going to say 4s2, 4p6, and then it's going to end with 4d3. Now, as a quick reminder, if we're doing orbital notation, that's the arrows for the opposite spins. Again, the s orbital has one room with 2 arrows, 2s, 1 room, 2 arrows, or 1 orbital, 2 arrows. I'm saying rooms because those of you that had me last year for honors remembered I used a room analogy, but this is the orbital. The individual orbitals are the rooms. The sublevel is the S, P, D, and F sublevels. Okay, so this is then going to the P, which has 1, 2, 3 individual orbitals. And remember, we spread them out before filling up, and that's because of Hund's rule. H-U-N-D, Hund. Hund's rule. Okay, then we go to our 3D level here, which would show the D's. There's 1, 2, 3, 4, 5 orbitals. And I'll double those up because we've blown past that. Then we go to the 4s. There's 1 orbital. 4p, 1, 2, 3 orbitals. And then the 4d. Now, 4d, again, is going to have 5 orbitals normally, okay, which I'll show here. In this case, we're going to spread them out. And so we have this being shown. Okay, so this is what the orbital will look like for the electron configuration for MO3+. Okay, that's it. Hope that jogs some of your memories. Okay, have a good day.